What if the vast expanse of the universe, far beyond our solar system, was not beyond our reach? Is this a dream or a foreseeable reality? This question has captured human imagination for centuries, a fascination that has been vividly portrayed in countless science fiction movies. From the moon landing in First Man to the daring rescue mission in The Martian, these narratives tantalize us with the thrill of venturing into the unknown. Yet the reality of such journeys is far more complex. The distances involved are staggering. Consider this, even the closest star to us, Alpha Centauri, is 4 light-years away. That's over 25 trillion miles, and our fastest spacecraft would take thousands of years to reach it. The harsh truth is that our current technology limits us to exploring only our immediate cosmic neighborhood. The first hurdle in this ambitious journey is speed, far beyond what we have achieved so far. In the late 1950s, NASA's Orion project proposed a bold yet dangerous solution using nuclear fuel. This audacious plan was to harness nuclear explosions as a means of propulsion, thereby reaching a staggering 3.3% of the speed of light. To put that into perspective, the speed of Apollo 11 was a mere 0.0037% of light speed. The Orion project was a quantum leap in terms of potential speed, but with such power comes substantial risk. The Orion project didn't propose using just 1 or 2 nuclear bombs. No, to launch a spaceship beyond the Earth's atmosphere and towards the stars, it would require a minimum of 800 nuclear explosions. Imagine that for a moment, a spacecraft being propelled by hundreds of nuclear detonations, each one more powerful than the bomb dropped on Hiroshima during World War II. Such a plan wasn't without its critics, and for good reason. The potential for disaster was enormous. If even one of these nuclear bombs malfunctioned during the launch process, the resulting fallout could be catastrophic. And even if everything went according to plan, the sheer amount of radioactive fallout produced by the numerous nuclear explosions would have been immense. This fallout wouldn't just disappear. It would linger in our atmosphere potentially for decades or even centuries. The health implications for life on Earth would be severe, with increased rates of cancer and other radiation-related illnesses. The environmental impact would be equally devastating, with the potential for widespread ecological damage. Despite its potential, the Orion project was shelved due to the risk of catastrophic fallout. The dream of using nuclear fuel for space travel wasn't dead, but it needed a new, safer approach. The search for a viable solution continues to this day, with scientists and engineers around the world dedicated to making interstellar travel a reality. As we look to the stars, we must remember the lessons of the Orion project and ensure that our reach for the heavens doesn't bring harm to our home planet. In a quest for safer alternatives, the Space Ramjet project emerged, aiming to utilize the hydrogen drifting in space. This innovative project sought to harness the vast, untapped resources of the universe itself, specifically the cosmic hydrogen floating in the vast expanses of space. Unlike the Orion project, which involved carrying heavy nuclear bombs, the Ramjet project offered a fresh perspective. The beauty of this concept lies in its simplicity and potential efficiency. By using the hydrogen atoms scattered in space as nuclear fusion material, the weight of the spacecraft could be drastically reduced. With less mass to propel, the speed of the spacecraft could theoretically reach up to 30% of the speed of light. Now, to put that into perspective, it's around 10,000 times faster than the speed of the Apollo 11. Imagine what humanity could achieve with such speed. However, as with many revolutionary ideas, there are challenges to overcome. The major hurdle for the Ramjet project lies in the practicality of collecting a sufficient amount of hydrogen to be used as nuclear fusion material. While hydrogen is the most abundant element in the universe, its density in space is incredibly low. Gathering enough of this elusive element to fuel a spaceship is a daunting task, to say the least. Moreover, even with the ability to reach 30% of the speed of light, interstellar travel remains a long-term commitment. The distance to Alpha Centauri, the closest star to the solar system, is 4 light-years away. Even with the Ramjet's impressive speed, a journey to Alpha Centauri would take over 13 years. And let's not forget, that's just the closest star. The distances only get larger from there. The Ramjet project, while promising, still left us with journeys spanning decades to even the nearest stars. Einstein's theory of relativity put a universal speed limit on our dreams of interstellar travel. This theory, proposed by Albert Einstein, is a cornerstone of modern physics, and provides a profound understanding of the fundamental laws of the universe. It also sets an apparent limit, the speed of light, a speed that no object with mass can ever reach. According to Einstein, as an object accelerates closer to the speed of light, its mass increases, not just by a little, but exponentially. Imagine our spaceship hurtling through space, its mass growing ever larger, demanding more and more energy to maintain its speed. At the same time, time aboard the spacecraft would begin to stretch, slowing down relative to the time experienced by observers back on Earth. This phenomenon, known as time dilation, would mean that passengers on a light-speed voyage might age mere years while centuries pass by on Earth. This paints a pretty bleak picture for our dreams of star-hopping across the galaxy, doesn't it? But here's the thing. While the speed of light is a limit, it's not considered an absolute barrier. Even Einstein himself said, imagination is more important than knowledge. And it is this spirit of imagination that has propelled scientists to look for loopholes in these seemingly ironclad laws of physics. Ongoing research is exploring the potential of warping space-time itself to create shortcuts like wormholes, or to manipulate the space around a spacecraft rather than accelerating the craft itself, a concept known as the Alcubierre drive. These are just theories for now, and they come with their own set of challenges and paradoxes, but they represent a refusal to accept that the stars will forever remain out of our reach. So, while we might not be packing our bags for Alpha Centauri just yet, we are not giving up. The universe is vast and mysterious, and human curiosity is limitless. Einstein's theory of relativity may have put a speed limit on our galactic ambitions, but even Einstein's limit has not deterred scientists from dreaming bigger. Wormholes, a concept more at home in science fiction, may hold the key to faster-than-light travel. These fascinating features of the cosmos are essentially shortcuts through the fabric of space itself, potentially allowing beings to traverse billions of light-years in a single breathtaking leap. Imagine an ant on a piece of paper trying to reach the other end. It could follow the surface, a slow and arduous journey, or the paper could fold, bringing both ends together. Suddenly, the ant's path is significantly shorter. That's, in a nutshell, how a wormhole would work. But of course, reality is a bit more complex than a folded piece of paper. The idea of wormholes is not without its challenges and dangers. The intense gravity within a wormhole could crush an unsuspecting traveler, while the enormous amounts of radiation might scorch them to a crisp. It's like stepping into a cosmic blender that's been supercharged by a nuclear reactor, not exactly the ideal vacation spot. Yet these seemingly insurmountable obstacles have not dampened our curiosity. In fact, they've stoked the fires of our imagination. The concept of wormholes has been a staple of science fiction, from novels to films, painting vivid pictures of interstellar voyages and cosmic adventures. One of the most notable proponents of wormholes was Kip Thorne, a renowned physicist from the California Institute of Technology. In 1988, he proposed the idea of a passable wormhole, a cosmic tunnel that could feasibly be navigated. His work sparked a new wave of interest and research into the concept, bringing it a little closer to the realm of reality. Despite the challenges, despite the unknowns, the concept of wormholes and faster-than-light travel captivates us. It tantalizes us with the promise of bridging the vast cosmic distances, of reaching far-off stars and galaxies, of truly becoming a spacefaring civilization. Whether wormholes remain a concept of fiction or become a reality, the human pursuit of interstellar travel continues unabated. We dream, we explore, we innovate, and who knows, perhaps one day we'll find our way through the cosmic labyrinth and into the stars. As we stand on the cusp of a new era in space exploration, what does the future hold for interstellar travel? It's a question that teases the imagination, daring us to dream of the seemingly impossible. We've explored the challenges, from the immense distances that separate the stars to the limitations imposed by Einstein's theory of relativity. But we've also dared to dream of solutions, harnessing nuclear fuel or cosmic hydrogen, even flirting with the abstract concept of wormholes. Yet the reality remains that, for now, these solutions are more science fiction than science fact. But science fiction has a way of becoming reality. The Apollo missions, the Mars rovers, the International Space Station, all were once just dreams, just stories. So, as we continue to dream, to explore, to push the boundaries of our knowledge, who knows what the future holds? The dream of venturing beyond our solar system remains as alive as ever, driving us to continually reach for the stars,